Hi everyone, this is Emmanuel from AirTrain. So today I want to talk about an emerging theme in the language space, and that is the fact that small language models can achieve similar performance to large language models sometimes on specific tasks, and that has some consequences for the industry, and it's good news for everybody. So what do we mean by large and small? So a large language model is your typical GPT-3, GPT-4 with hundreds of billions of parameters. Llama 2, like from 7 to 70 billion parameters. Falcon from 7 to 180 parameters. So these are large models. A small model would be from a few million to maybe a few billion parameters. What is the problem with large language models? Well, they're very powerful. Obviously, they can generate some very high quality content. However, they are very expensive to run. They require a lot of GPU, a lot of memory, and they have also very high latency. So they're slow, they're hard to host, and also they most likely need to be fine-tuned to learn particular tasks, or to be part of a RAG chain, for example, to have private data input. So this makes them prohibitive to run in many cases if you don't have the hardware to run it. So for example, you cannot run it on a device, for example, it has to run on a large GPU cluster, and so on. So today we're going to look at two papers that sort of show what you can achieve with smaller models. So the first paper that I want to look at from Microsoft Research came out actually last week. It's called "Textbooks Are All You Need," which is obviously a joke on the original Transformer paper called "Attention is All You Need." So what they did is that they trained and then fine-tuned a fairly small model, so only 1.3 billion parameters, on a very high quality data set of coding exercises. So they're trying to do code generation, and they got some very high quality data from the web, but also they generated a billion token of high quality content using GPT 3.5. So they fine-tuned this model to do just that with this high-quality data set. And so this Phi-1 model here has very good performance. If we look at the HumanEval benchmark up here, so HumanEval is essentially coding problems. The way it looks is like this. It's a human-created data set where humans will sort of design those doc strings with some unit tests for each problem, and the model has to generate code to satisfy the docstring description of the problem. And the way to measure performance on this problem is using the pass at k metric. So the pass at k essentially measures the accuracy when k samples are generated for each prompt. So for example, pass at 1, we generate only one inference for each prompt, and we measure the fraction of prompts that pass the unit tests. If we look at how Phi-1 is scoring, so here we have Phi-1 with 1.3 billion parameter scoring a 51% accuracy at pass at 1, which compares to GPT 3.5, which is lower, 48%. Code Llama is about 48, almost 49%. And so on. Obviously, GPT-4 is still much better, but it's quite impressive that with a fairly small model, 1.3 billion parameter, they're able to achieve performance that is comparable to GPT 3.5, which has 200 billion parameter and is trained on a lot of GPU and for a lot of time. Phi-1, according to the paper, was trained for 4 days on 8 A100 GPUs. This is very small compared to the thousands of GPUs used by GPT 3.5 and the weeks of training. So this is pretty impressive. Here's another piece of evidence, another paper that came out back in April called TinyStories. So what they did with TinyStories is that they used GPT 3.5 and GPT-4 to generate short stories that can be understood by a toddler, like a 3 to 4 year old, essentially. And then they train those smaller models with like just a few million parameters to do text completion using those data sets. And the way they do evaluation is actually pretty interesting, is that they ask GPT-4 to grade the output on a number of scales. So for example, they will grade things like creativity, grammar, consistency, and so on. And so the results are pretty impressive as well. So here on the left, there is a prompt, and then the models are asked to complete the prompt. And we have here a whole bunch of fairly small models, like just from 1 million to 33 million. And on the right here, we have GPT-2 with 1.5 billion parameter. So obviously, with today's standard, this would be considered a small model, but compared to those really small models, this is a large one. And as you can see, those small models, this one doesn't perform so well, the 1 million parameter one, but with just less than 100 million parameter, you can have some very good performance. So that's much smaller than the 1.5 billion here. So let's look at an example. Alice was so tired when she got back home, she went home. Obviously, that makes no sense. Went to bed makes sense. And then even better is went straight to bed. And then GPT-2 just says went outside, which makes no sense. So as you can see, we get some really good performance here from a fairly small model compared to GPT-2. Why is this important, those two papers? It is important because we can potentially see a future in which people are using smaller models for very specific tasks instead of training or fine-tuning very large models. And so fine-tuning a very small model, can take just a couple days, for example, on a handful of GPUs. And so that means that also those models are going to be much cheaper and faster to run. They're going to require less memory, and which means that they can also potentially run on, your laptop or your phone or maybe your watch. And so that's really good news for the future of language models. So in the future, you could also think about the fact that we may use what they call mixture of experts, where you have a whole zoo of smaller specific models that are expert at a particular domain. And those models are sort of orchestrated by a larger model that tries to kind of route a particular prompt to different models, and then creates a sort of consistent response based on the response from all those smaller models. So yeah, this is great. You should probably look into smaller models if your task is very well defined. But one thing to remember is that those two examples, those two papers worked because the training data was high quality. So this is probably the biggest takeaway from those two papers, is that you need to have a very high quality data to get any sort of good output from those models. So you need to create your data set almost by hand potentially, or use synthetic data as they did to do this. Right, that's all I wanted to say for today. Take a look at those papers. The link is in the description, and subscribe to the channel. All right, thanks. Bye-bye.